Okay, good afternoon, everyone. My name is Leon Thiem. Russ Morgan and I are the instructors for CVE 498 at Capstone. This is their presentation. There are 4 teams that we're going to hear this afternoon. The order of presentation is going to be tags, anchor, steel stand, and ace. So without further introduction, I give you tags.
Good afternoon, everyone, and thank you for being here. My name is Captain Fanning, and I'm the project manager and structural engineer of Tags Engineering. Our team consists of 9 civil engineers, all of which who played a crucial role in the completion of this project. For our project, our client requested that we design both a restaurant, which seats 130 people, and 6 retail buildings, all of which have second-floor loft-style apartments. Our site is located in Tiverton, Rhode Island, on Mount Hope Bay, which is just north of the Secana River Bridge. Our site is actually located in a V zone up until the shoreline, and an A zone throughout the entire site with a 100-year flood elevation of 21 feet. Because of this, we have chosen to design all first floor elevations to 22 feet. Our existing grade on site averages to about 10 feet, so because of this, we had to add about 12 feet of fill throughout the entire site to meet our proposed grade. This is an example of what our proposed site plan looks like. Over there is where our restaurant is located, right by the bay. A little bit down the road is where our retail and residential buildings are. And as you can see, along the eastern side of our site is an existing railway, which the state requires we leave untouched for future use. So because of that, we had to design a bridge over here in order to gain access to our site. I'm going to let Dave talk a little bit more about our existing soil conditions.
My name is David Layers, and first I'll be talking about the existing soil conditions. The existing site elevations range from 40 feet at the east side of the site, gradually sloping down to the still water level of Mount Hope.
100 on the outside and 100 on the inside and 30 on the outside. This is a 3D model that I came up with to give you guys a better understanding of what our restaurant looks like. Out on the back deck is where people can sit, enjoy lunch, dinner, and a drink by the bay, and directly above that are solar panels which act as an awning while also acting as a green incentive. This is our column layout. Our whole structure is made completely of steel. Our columns are HSS 6 by 6 by a quarter steel tubes, all spaced evenly at 20 feet. As you may have noticed, there's no interior columns in the restaurant. This was designed intentionally this way to maximize our floor space. This is an example of what our frame looks like. While calculating the loads for the restaurant, I came up with a superimposed dead load of 34 pounds per square feet, a roof deck concrete slab load of 33 pounds per square feet. A snow load, according to building code in Tiverton, was 30 pounds per square feet, and our wind load was 62 pounds per square feet. After analyzing it, the structure was clearly controlled by the high wind loads. While designing this structure, we wanted to maximize the window space so customers could enjoy a nice view of the bay. So as you may have noticed, there's no cross bracings along the columns. Instead, we have moment frame connections connecting all the columns and the exterior beams along the outside. On top of that, we also have a 4-inch slab on grade with 6 by 6 W1.4 by W1.4 welded wire fabric. Now I'm going to let Dave talk a little bit more about the foundation of our restaurant.
Hello again, my name is David Layers, and now I'll be talking about the restaurant foundation. This is a soil profile developed for the proposed restaurant location, which may be seen at the top of the screen. The surface elevation here is 10 feet above sea level with the groundwater 5 feet below the surface. This will require 11 feet of structural fill to raise the restaurant above the 100-year flood elevation. With respect to the blow counts of the soil, this consists primarily of fine to coarse sands and gravels and uncontrolled fill, which must be compacted in place before any additional fill is placed on top of it. This is the restaurant footing layout, which is made up of 12 square footings and a grade beam between each column to carry the exterior wall loads. Each column footing must resist a lateral wind load of 25 kips and a vertical load of 70 kips. These column footings will be 4 feet by 4 feet, with number 4 bars spaced at 12 inches for steel reinforcing. These footings will sit above the minimum frost depth permitted by ASCE 32, since the footings will sit on free draining soil and the exterior walls will contain the proper insulation. Overturning, sliding, and bearing capacities of these footings were designed with a factor of safety greater than 2, and the ultimate settlement in this restaurant will not exceed 1 inch. Now I'll turn it over to Brandon, who's going to talk about the retail and residential buildings.
My name is Brandon Moore, and I was a geotechnical and structural engineer on this project, and also AutoCAD specialist. We designed six two-story retail residential structures of 1,000 square feet each, which will be grouped in pairs with phase construction. The first floor is designed for commercial spacing to be utilized for retail. Above these will be luxury-style apartments consisting of a balcony overlooking the water. The current elevation at this location is 13 feet above sea level, with a groundwater table 8 feet below the surface and a frost depth of 3.5 feet. The soils here consist of fine to coarse sand above weathered sandstone. As Kevin said before, the flood elevation is 21 feet, so the first floor will be designed at 22 feet, which will require approximately 9 feet of structural fill. We calculated a 97 kip lateral wind load, which will control the design. Similarly to the restaurant, the foundation plans will also consist of 4 feet square footings, with the exception of 3 feet square footings below each staircase. The retail residential buildings are steel frame structures with cross bracings to reduce the lateral wind load. Now Tom's going to talk about bridge abutment and retaining walls.
My name is Tom Ferranti, and I was a geotechnical engineer on the project, and I'll be talking about the bridge abutment and the retaining wall. So the bridge abutment is located right here on the site, the west approach, where we had a surface elevation of 34 feet and a groundwater table that was roughly 29 feet below the ground surface. Okay. When designing this bridge abutment, we used both LRFD and ASC load combinations with a resistance factor of 0.8. We had an abutment height of 30 feet, which prevented both sliding and overturning, and abutment footing width of 14 feet, which, we had an abutment height of 30 feet. We had an abutment height of 30 feet, which allowed for ride out right away and minimized the slope on the bridge. And we had an abutment footing width of 14 feet, which prevented both sliding and overturning. And we had ultimate settlement of 1 inch in this area. Okay, so as you can see here, we have the design for the bridge abutment. 30 feet high, 14 feet wide in the bottom, and 2 feet thick all the way through. For reinforcement, we had main rebar placed at 12 inches, number 4 bars on the front side, and number 10 bars at 6 inches on the back side. And we had temperature and shrinkage rebar. Number 4 is at 12 inches on the front side, and number 6 is at 12 inches on the outside. I don't know what's going on with this. Okay, for the retaining wall design, the retaining wall is the green area that runs along the side of the road. It starts at an elevation of 56 feet and goes down to an elevation of 36 feet, where it ties into this existing grade. It's 250 feet in length along the outside and 190 feet in length along the inside. And it follows an 8% road slope, which goes down to the existing grade. We use the same rebar in the retaining wall as we did in the bridge abutment. Okay, like before, we had LRFD and ASC load combinations taken into account when we designed the retaining wall, and resistance factor 0.8. The footing of the wall will span from under the abutment down to where the road meets existing grade, and this will prevent sliding and overturning. And we will use free draining soil to fill behind the retaining wall, along with 4-inch PVC piping spaced at 10 feet to allow for drainage. I will now pass it on to Peter, who will talk about the bridge.
Hi, I'm Peter Savage, and I'm the structural engineer for Tegs Engineering, and I'll be speaking on the bridge. The bridge is located at the southeast end of the site, and will be constructed due to the existing railway under the bridge. That will remain active. Here's a 3D schematic of the bridge, showing all its components. The bridge, it's 42 feet long and 32 feet wide bridge span, which consists of two 12-foot lanes, one 5-foot sidewalk, and two parapet walls on each side. Beneath the bridge, there's a vertical and horizontal clearance of 26 feet and 40 feet for both the railway and the bridge and the bike path. In attaining all design requirements, AASHTO, LRFD, ASE, and the RIDOT bridge manual were all referenced. After all calculations, we resulted with a live load of 1120 pounds per square foot, a truck load of HL93, formerly known as HS20, and a dead load of 460 pounds per square foot. From those loadings, we designed the bridge with an 8-inch thick concrete deck and a number 6 rebar in the concrete deck at the top and the bottom, spaced at 12 inches, and a W18 by 16 beam spaced at 4 foot each. Here's a cross-sectional view of the bridge showing all its components. Here's the two 12-foot lanes, the 5-foot sidewalk, and the parapet walls, the W18 by 60 beams, and that's the 8-inch deck where the rebars will be placed. And now I'll pass it on to Brian Loth to speak on the site grading.
My name is Brian Loth, and I was the site civil engineer and AutoCAD specialist for this project. For the site grading on our project, we had a few difficulties to start out with. Since our site is so low in elevation and we needed to build a bridge connecting to the existing road, which was at 64 feet, we had to go from 64 feet to a 22-foot elevation, which was for the retail and restaurant due to the 100-year storm requirements for FEMA. And because of that, there was an 8% slope on our roadway entering the site. So for grading, we had a 4% slope wrapping around the boundary of our site and also in the retaining pond. And for ADA requirements for our lawn seating over here, we had a slope less than 5% to accommodate people to sit and watch performances on the stage. Here are our two horizontal curves for our site. Our roadway is 1,300 feet long, and we determined a design speed of 20 miles per hour for this site. Normally the design speed would be, we determined a 20 mile an hour design speed for our site. Normally this would be 25, but since our slope is so steep entering the site, we put it down to 20 miles per hour. Also, that accounts for speeding. And for our site, the minimum turning radius was 65 feet, and our larger horizontal curve was 150 feet, and the two radii for our smaller horizontal curves met the minimum at 65 feet. Here's the first part of our vertical curve on the site, and up here was where we matched our proposed road to the existing road, and there's an 8% slope over here, meeting the 62-foot elevation down to our restaurant elevation, which is around 22 feet. This is the second part of our vertical curve, and running throughout our site from south to north, there towards the end of the site, around here, there was a 1.5% slope, and around here was the low point of our road at elevation 18, which help for drainage into the retention pond. For the pavement design for our project, we used a typical Rhode Island deep strength pavement, and some assumed data values were we used 100,000 ESOL value, we used 15 KSI residual modulus, an ADT of 500, and we also used a 90% reliability. And for our pavement design, we used 2-inch asphalt surface, 6-inch asphalt base, 12-inch granular subbase, which was all on top of subgrade soils, which in the case of our site was compacted fill. Now I'm going to turn it over to Mike Harrison, who talked about parking.
Hello, I'm Michael Harrison, and I designed the parking on the site. There are 4 different parking areas on the site. We have one for the restaurant, which is the bigger one. There's one for the employees, which is right next to the restaurant, and there's also a smaller one for the retail and residential, and there's also a really small one all the way to the right side for the boat ramp. For the restaurant, we have chosen 96 spaces because according to the Tiverton Code of Ordinances, Appendix A, Article X, we need a minimum of 33 spaces because you need a car space for every 4 seats, and we have 130 seats. So we greatly exceed that requirement with 96. The reason that the number of parking is so high is because we expect that there could be events in the lawn seating area, which could draw in crowds. We also have 4 handicap spaces. This meets the American with Disabilities Act accessibility guidelines. That states that we need 1 spot for every 25 spaces. Restaurant employees will have 24 spaces, 22 spaces, with 1 handicap spot also, and the retail and residential buildings will also meet Article X's requirement by having exactly 20 spaces. There's also 1 handicap spot in this space. The pavement for the parking will be the same asphalt pavement in which Brian mentioned before. Each space will be 9.5 feet by 18 feet parking, which meets the requirement of 9 by 18 feet. Also for the parking, we use solar lights. There will also be a walking path on the site. It will go all the way around the site from the lawn seating area to the restaurant, to the retention pond, all the way to the boat ramp. The walking path pavement will use I2 pavement mix, and solar lighting will also be used around the walking path. And I'm going to give it to Sam, who did the REVETMENT design.
Good afternoon. My name is Sam Osei, and I worked as the transportation and marine engineer on this project. As you can see, our site is located right by the bay, and because of this caused concern for our shoreline as far as waves, erosion, and just possible destruction of our shoreline over time. So we decided that we would design a revetment in order to protect and preserve our shoreline. Because we are located in a flood zone, I was able to access the FEMA flood insurance study report for Newport County, for the town of Tiverton. And this data was collected using the 100-year 1% still water level. And I was able to retrieve the necessary values from this resource. For the design, I was able to use the United States Army Corps of Engineers shore protection manual, which was essential in the design of our revetment. I also had to choose a geosynthetic fabric, which would be able to protect our soil from any possible degradation. This is a typical cross-section of a revetment design. As you can see here, our still water level was found through FEMA to be, the significant height level was found to be 4 feet. And for the design, we worked in accordance with the Army Corps H10 and found the design height to be 5.08 feet, which is just 27% higher than the still water level on our site. We used a slope of 1 to 1.5, as the Army Corps didn't recommend anything much steeper than that. We also chose to use two layers for our armor stone. These 2 layers were comprised of rough quarry stone, and the weight was 1,942 pounds each. The thickness of our armor layer was found to be 4.56 feet. We also used an underlayer located right in this area, all the way throughout the revetment, which was 1.25 feet. This layer would be comprised of smaller stones to filter out, and will be made up of 2 layers of 8-inch stones. Overlaying our soil will be Marafi geotextile fabric. This will be used to protect and filter, and also just to protect the soil from any degradation over time. We believe that this design is sufficient and adequate enough to keep our site pristine and attractive to our patrons. I'm going to turn it over to Connor, who's going to talk about our environmental aspects.
Good afternoon. My name is Connor O'Halloran. I was the environmental engineer on the project. I'm going to talk to you about stormwater and wastewater. To begin with, at the downstream end for stormwater, a stormwater treatment was selected of a wet vegetated treatment system to meet the Rhode Island DEM Stormwater Manual Section 3.3.3 and the water quality volume of 78,205 gallons. This is the amount of stormwater runoff which is required to be treated on the site. The WVTS was sized to have a capacity of over 82,000 gallons. Directly upstream was a sediment forebay. To meet the Stormwater Manual Section 5.2, the forebay must be able to have a capacity of 10% of the water quality volume. To meet this sizing requirement, we sized the sediment forebay at 20 feet by 20 feet by 4 feet deep. This would give us a design sizing capacity of almost 12,000 gallons. A hydrodynamic separator was suggested from Contech Engineered Solutions. The model Vortex 16,000 features a large swirl chamber capable of particle removal of down to 50 microns, baffles to remove floating hydrocarbons, as well as high and low flow controls to manage residence time. Conveyance piping was sized using the rational method and Manning's equation. The pipes range between 12 inches and 36 inches. 12 inches at the southern end of the site where there's large slopes, and all the way up to 36 inches at the flatter portions of the site. All calculations, were based on the 100-year storm event. Wastewater. All wastewater will be pumped off-site to the Tiverton Municipal Sewer System, tying in at the Route 138 and Sousa Road interceptor. The wastewater daily design flows of 5,200 gallons per day from the restaurant and 2,500 gallons per day from the retail residential will travel to a pump station via 6-inch gravity-fed pipes and be pumped uphill via a 4-inch main. To overcome the static head, friction, and minor losses, the Fristam FPR 3542 pump was selected, pumping at 250 gallons per minute at 240 feet of head. This pump can meet the Tiverton Sewage Disposal and Sewers Code, Section 18-4 and 18-5.4. I'm going to turn it back over to our project manager, Kevin.
Thank you. I'd just like to give an extended thank you to Steve Cabral, Bob Fairbanks, John Steer, Brian Giroux, Russ Morgan, and Professor Thiem for all their assistance on this project. And with that being said, I want to leave the floor open to any questions.
What was the 100-year still water elevation? What was the elevation of the first floor of your buildings?
Yeah, 22 feet was the level of our first floor elevations. The flood elevation was 21 feet. And what was the still water elevation? Still water was 16 feet.
David.
Yes.
One of your slides indicates that we have sufficient bearing capacity soil.
Yeah.
Can you elaborate how you can say we have sufficient bearing capacity in your site?
I don't have the exact numbers off the top of my head, but it's all in our report, our calculations.
What kind of method did you use? I mean, you got information, and then what kind of method they use, or if you did yourself, what kind of method did you use?
We used ASD, and like I said, at the factor of safety of 2, and we used Terzaghis equation to determine the bearing capacity, and
My understanding is you start with the boring data, right?
Yeah.
Can you did you see any evidence from the boring data or testing data, anything?
Well, all the borings showed really high blow counts, so almost all the existing material was very dense. The only thing that we weren't sure of is that some of the uncontrolled fill at the surface, which would need to be removed, replaced, and compacted to maximum dry density.
Well, then let's move it to Brian. Brian, you designed the pavement. So that's also related to the bearing capacity or property of subsoil soils. How did you determine the bearing capacity or properties of subsoil soil?
Well, pretty much our site has medium dense to very dense soils, and on top of that would be compacted fill. Because of the 8% slope of our roadway, we would have to raise up the elevation, and also for FEMA. But I pretty much used all of Dave's calculations to determine that the pavement would be sufficient for the site.
So, when you design pavement structure, what kind of parameter you are using for the subsoil soil?
Compacted fill. That we
Engineering the properties.
Subsurface engineering properties.
Engineering properties of subsoil soil.
I don't know off the top of my head, but it's all included in the report.
Thank you.
Okay, well, thank you very much.
Guys, just help us grab these.
I'll grab this.
Anchor Engineering is next. Yeah.
Clickers are
Where?
I'm going to sabotage the system.
Huh?
Good luck.
I appreciate that. You didn't answer any questions.
Me? What are you talking about?
Any specific questions by Lee? Huh? It will just. Yo, just have it right there and I can show it.
Hold this.
Where's the other one?
I don't know. That one. Still find that driver. Yeah, I thought they'd be nice and let us use their computer, but yeah.
Didn't show.
Didn't foresee this. If you want to try, yeah. Yeah. Let's try this. Yeah, grab his laptop then.
There's the old one. Well, let's keep the old one.
You serious? It's not in there.
Just so it's right there.
We'll put on his right away.
What's it under? Anchor Engineer and Final Presentation?
Yeah, and then this is for like.
No, don't.
We don't need to click.
You don't need that.
All right.
I don't know if you did or not.
We got it. So you just need to connect the computer now. As long as it shows up on the screen, we're in business.
Do it last time. It's easier. It's on the flash.
I don't know how to really work all this. Hold on, it's gonna come. Is that actually plugged in? Every good group brings its ass up loud. That's preparation at its finest.
All right, good afternoon. I apologize for that delay. And welcome to our final presentation. My name is Brett Nealon, and we are Anchor Engineering. All right, so throughout the past year, we have been assigned to develop a site by our client, Mr. Mark Fisher, in Tiverton, Rhode Island. This site's deliverables were as follows. To extend, well, we were given the virgin site to develop. We needed to extend Schooner Drive down to meet the site. We needed a bridge to get across to the site. We needed to construct parking for the designed retails, 6 of them, 3 for current construction and 3 for future. And we also needed to design a waterfront restaurant. I will now be giving it off to Chris to discuss the proposed site.
Hi, my name is Christopher Rogers. I was the AutoCAD specialist in site development lead. To begin with, we have our site right here. Bottom, we have the bridge that starts off to get to the site itself. As you continue down, the first thing you see is the restaurant, so it's the first appeal when you first come down the road. Continues forth to the primary parking lot. From there, you continue forth to get the secondary parking lot, of which behind it is the retail and apartments. When you continue forth, you have the turnaround for emergency vehicles and for boats that want to turn around. When you go further, there is the parking for the boats, and then the boat ramp right there. On the west end, we have the restaurant that's closest to the water, and wrapped around the entire thing is the pathway. This is for the existing proposed grading. On the north and south end, we tie into the existing grade. Our main objective was to take most advantage of the water scene. That's the primary objective on the Tiverton waterfront. So, along the south end, we have the first bridge. Next to it is the retaining wall. That's where we can have the different slopes and grades. From there, on the actual where the restaurant is, we have a flat slope. When right after the pier, it drops down so it looks you can see right into the ocean itself. When you continue forth, on the retail we have a slight slope so the water continues forth down to the detention pond on the north end. And on the west end we have a breaking rock wall that allows us to break the different grades. We have 3 retaining walls, 1 from the primary on the primary parking lot, 1 in front of the restaurant, and 1 on the far end to break for the turnaround. Now I'm going to go over to Brian Levy to talk about roadways and parking lots.
Good afternoon, I'm Brian Levy, and I did transportation for the project. As you can see, the road starts off at an elevation of 50 feet. It's connected to Schooner Drive and wraps around the restaurant to the primary parking lot, the residential and the retail lot, and finally the boat parking lot right next to the boat ramp. The total length of the road was 1,640 feet. It was designed to Rhode Island Department of Transportation standards with a design speed of 25 miles per hour. The grade at the entrance is pretty steep, and it eventually, as Chris talked about, flattens out into the existing grade. The asphalt we used was recycled because it'd be cheaper and easier to construct. These are the cross sections of the roads. As you can see, the asphalt concrete surface is 1.5 inches. The sub base is 6 inches with, and then the base underneath that is 12. The sidewalks are 6 feet in length and 6 inches off the curb. The shoulder of the road too is 2 feet to provide a little bit of safety for pedestrians because there will be a lot of people walking around on the site. And the For the parking lots, we have the primary. The primary one has 93 spaces with 8 handicap spots for people who need those. Retail and residential has 43 spots with 12 set aside for the residents that live there, so they'd have like stickers on their vehicles. And finally, the boat parking lot has 8 spots available for the trucks and their trailers. The sizes of the spaces are 9 by 18 feet and 10 by 40 for the boats. And now I'm going to go off to Eric O'Brien for the soil profiles.
My name is Eric O'Brien. I was one of the geotechnical engineers on the site. My first priority was to get an idea of the pre-existing material on the site. In order to accomplish this goal, we were given a series of 30 boring logs, from which I created 4 soil cross-sections. The locations of the cross-sections can be seen in the upper left there. The one I included in this presentation is cross-section B. It runs approximately east-west on the northern end of the site. And from these cross-sections, we can see that the surface soil on the site is fairly dense but uncontrolled fill. It's filled with a lot of debris, boulders, pieces of wood, trace organics, so I did not consider it structurally sound. Fortunately, since we need to raise the grade of the entire site above flood levels, that gives us plenty of room to fill in the site with structural fill. Another consequence of raising the site is that any water table concerns that we may have had are mitigated unless we are building close to the shore, but any of our major structures are built on much better material. My second task was to design a retaining wall. The wall I chose to design runs approximately where that soil profile is located, so that's just north of the retail development area. This is a fully reinforced, typical cantilever design built to comply with Rhode Island State Building Codes and ACI 31808 specifications. It was important to us that this be fully draining, which I accomplished through the pervious backfill and PVC weep holes placed 10 feet on center. This supports the open grass area, and there's actually open grass area on the other side that runs down to the pond, so it was important that this drained freely. I designed it conservatively so that it could be installed and backfilled and remain stable without any soil over the toe. I did this just to aid in the construction of the retaining wall. I also performed a cost estimate on the installation of this wall. I'll run through this quickly, just give you an idea where some of these numbers came from. All the earthwork quantities I calculated myself using the soil profile I showed you, the cross-section I showed you, and the proposed grading plan. All of the earthwork unit prices came from the 2013 RIDOT weighted average unit price database. Man hours were calculated using formulas found in the estimator's general construction man hour manual, and hourly wages are the prevailing wage interpreted for the appropriate operator or laborer needed to complete that item. In total, the cost of installing a retaining wall was around $54,000, and I actually also calculated the cost using just the retaining wall item in the weighted average unit price database, and the two numbers were within $200. So this appears to be a fairly typical cost for a retaining wall of this size. Next, I'll hand it off to Mason for the environmental engineering portion.
I'm Mason Martini, and I was the environmental engineer for Anchor Engineering. My first task as the environmental engineer was to handle the stormwater, deal with some stormwater controls. My main rules and regulations guidelines in Rhode Island was the Rhode Island Department of Environmental Management's standard stormwater design and installation standards manual. These 24-hour rainfalls come straight out of that manual. These will play a key role in designing stormwater control. We had 3 main ways to deal with the stormwater. We used permeable paving in the parking areas. We used storm drains and conveyance piping to the detention pond on the roadway. And we had a swale on the east end of the site for overflow protection from the apartment complexes above. This is the utilities plan. As we can get a close-up, oops, sorry. We can see the red is the conveyance piping from the roadway. We have storm drains tying in, and we have permeable paving in this main parking lot, and we also have it in the retail and apartments. The swale is on the bottom of this picture here. and the detention pond is on the far end, the north end of the site. The permeable paving has to be designed to a 100-year storm plan, which for Newport County is 8.6 inches. So the volume of the voids for this pavement has to hold 8.6 inches. We used crushed stone to account for the majority of this, which has a void ratio of about 0.45 to 0.5. I used 0.4 in my designs to be a little conservative. And this is what a typical cross-section would look like in our parking. The conveyance system was the hardest system to design. It required a lot of factors. We had to use equivalent areas, runoff coefficients. I had to constantly change the time of concentration as the pipe flow along the system and use the intensity, duration, frequency charts for Rhode Island. I also had to use pipe flow charts to size the pipes and make sure that the velocities and slopes were proper. We ended up using 12-inch piping for the majority, and then about 3/4 of the way through, it switched up to an 18-inch pipe, where it goes to a flared end into the detention pond. The detention pond is required for treatment of the water quality volume as outlined in the manual I mentioned earlier. You need to treat the first 1 inch of runoff. To calculate this, you multiply 1 inch by the impervious area, which was the roadway. We needed to account for 3,000 cubic feet of treatment. Our pond is designed to hold 3,300 cubic feet, so we exceed that value. Next, Ben Pickering is going to talk about the bridge design.
Good afternoon. My name's Ben Pickering, and I was the structural engineer for Anchor Engineering. The first thing I'm going to discuss is our bridge design. The bridge is the first thing you cross when you come into our site. The first thing I'm going to go over is just a few quick dimensions. It's 2 lanes, 12 feet wide each. There's a sidewalk that's 6 foot wide, 6-inch curbs. We made our deck out of concrete. This was 8 inches thick, and there's railings on each side for safety purposes. The next thing I'm going to talk about is the structural integrity of the building. We went with beams that were W27 by 114 and joists that were 30K12. The beams were calculated through tributary areas and factored loads. This allowed me to calculate moments and allowed me to get the beams I needed from the ZX tables. Those are made out of A992 steel. As far as the joists, this was done in a similar fashion with tributary areas and factored loads. And from there, I selected the joists, and those are made out of A36 steel. A few things to notice is the span, the height of the building met the requirements for the train, and the width of the building also accommodated for the bike path and the train. Next to talk about the bridge abutments is Eric City.
Good afternoon, my name is Eric Chankalima. I am a geotechnical engineer for Anchor Engineering, and I designed this bridge abutment. A couple of goals that we wanted to meet for the bridge abutment was to allow horizontal clearance for the rail system and the bike path to be added to the site in a future instance, as well as vertical clearance for the rail system itself. The bridge abutment was designed as a mechanically stabilized earth wall. The reason we decided to go with this type of design is due to the fact that a traditional gravity retaining wall would have such a large footing, it would extrude below the rail system adjacent to it that would be included in a later date. This would exert unpredictable loads that would possibly make the gravity retaining wall unstable. By going with the MSC design, we could omit the footing altogether due to the fact that the reinforcement members take most of the strain. The bridge abutment requires 25 feet of clearance to accommodate the rail system. We built it up to 30 feet with 20 blocks offset at 0.2 feet apart. There are 10 geo-reinforcement grids placed 3 feet from each other along the Z-axis. These reinforcement members required a minimum of 7,000 pound-foot forces per feet squared. They also have a reinforcement length of 35 feet. Now I'll pass this back to Ben Pickering for restaurant design.
Once again, my name is Ben Pickering, and I'm just going to briefly talk to you guys about the restaurant design now. Our goal was to provide our client, Mark Fisher, with a scenic structure that would be appealing to customers. It was designed to seat 100 people inside, 40 people outside. A few things you can notice about the layout is that in the west corner, you got the dining, that's where the water is. In the northeast corner, you got the entrance, that's where the parking lot was. As far as the integrity of the actual structure, we went with columns and beams on the outside of it. The beams we used were a W21 by 50. We kept this consistent throughout. This was due to constructability purposes. This was calculated similar how I just mentioned with the bridge through factored loads, and then I went into the ZX tables and selected from there. Those were made out of A992 steel 50 KSI. As far as the columns, we went with tubes, HSS 5.5 by 5.5 by 3/8. This was used throughout the whole building except one column. The one column we went with was the interior column. That was a tube in 8 by 8 by a quarter. The reason for this is this column carried much more load. These were calculated from point loads coming in from the concentrated loads from the beams. We used joists throughout the whole restaurant. The top section you can see 24K by 12, the bottom section 26K by 7. These were spaced 5 feet apart, and these were calculated through tributary areas and factored loads. As far as the wind load goes coming into the building, we had to design a cross bracing. We put a cross bracing on all 4 sides of the building. This was calculated through the wind load coming in, and then I took the force on the diagonal to see how many kips it held. In the end, we calculated this out to be an HSSS 4x4 by 0.25 tube. This picture depicts the wall and roof cross section. The interesting things to note here, we went with a parapet design on the top of the wall, and we actually indented it 4 feet in and made a slant coming off. This was done for a variety of reasons. One's drainage, and the second reason, which is important, is it takes away from a flat, square building. It gives it a little more appeal to customers coming in. This picture is the actual roof and how the drainage works. We went with a flat roof, but it's still at high points. All the circles you see, those represent the high points, and the arrows represent where the drainage goes. The drainage would go into gutter systems, and the gutter systems would flow down the columns. This would help hide the gutters to customers that would come into the restaurant. And this is basically what the finished product would look like. You can notice the west face, that's where most of the main dining is. That's where we put a lot of glass. And then you can notice the slants from the parapet, how it takes away from the box look of the building. Also, an interesting thing we did is with the entrance, which you can see in the west face, we made it slightly lower than the rest of the building. This way, when people come to the restaurant, they clearly know where to go. Next is going to be Eric O'Brien to talk about the foundation plan for the restaurant.
All right, so we have a fairly light single-story structure, so the foundation plan is very simple. We're looking at a 4-inch thick floating slab on grade surrounded by a continuous foundation wall that thickens up around the exterior columns to form the footing for those columns. And there is an isolated square footing underneath that central column. I've got a couple of cross sections here. So the interior footing is slightly larger to hold that larger load from that column, but otherwise the designs are largely the same. They're both designed for minimum steel reinforcement because of the light loads. We included a 4-inch shelf to rest the foundation on, and we thickened it up. This is because a portion of the wall hangs out over that foundation and actually rests on it. Up next is Brett Nealon with the retail design.
Again, my name is Brett Nealon, and not only was I project manager, I also did some structural aspect to the project. I focused on the retail and the apartment building. The bottom floor, seen to the right, is the retail, and the left is the apartment. For this design, I decided to go with a timber design using southern yellow pine. Excuse me. I designed the header to be 11.5 by 11 and a quarter by 5.5. This was done for the deflection and the support of the studs, which were calculated to be 2x6 at 16 inches. To the right is just a wall section showing the support and the studs. Now for this building, as you'll see in the next slide, there's a lot of windows. Due to this and the wind load, which is 31 pounds per square foot, I had to take into account a strong wall or a moment bracing. As seen to the left, I'll show you the elevation view in a second. Because of the pitched roof, I had to indent the steel framing, adjusting the support. I did this with a software done by a timber design company online. The truss seen to the right is for the pitched roof. The truss had to be brought up due to the elevation clearance of the second floor. This is the elevation of the proposed design of the building. To the bottom right is the moment framing that I was talking about. Just too many windows and doors for a cross bracing. I will now turn it over to Eric C. for the footing.
Good afternoon again. My name is Eric Chantalima. The foundation plan is a standard 4-inch concrete slab supported by 6 columns, one at each corner and one at the midpoints of each wall. Now the foundations are similar dimensioned square footings. It's a 5 by 5 foot base at a depth of 3 inches. Now, the reinforcements for the four footings at the corners would be 6 number 11 bars spaced at 10 inches with a 3-inch cover, and the reinforcements for the midsection columns would be 6 14-inch bars by spaced at 10 inches on center with another 3-inch clearing. And now I'll pass this to Mason with the wastewater.
Alrighty, as the environmental engineer, my second main focus was wastewater management. We had 2 options. We could treat the wastewater on site, or we could pump it to the main sewer line. Due to the industrial loading and the large loading from the restaurant, we thought it would be best to pump it off to the sewer line. My main set of rules and regulations came out of the Department of Environmental Management's on-site wastewater treatment systems rules. Though we pumped it, a lot of our calculations we had to get from this manual. This was the total demand for the site. We had about 6,500 gallons per day, which broken down per hour isn't very much. We had a peak hour factor for such a low population zone of 4, which makes our peak hour demand very high. And we need to pump 18 gallons per minute at the peak hour. This is important for the pump design that I had to do later on. This is the utilities plan. We get a close-up. This yellow is the sewer line. We have, coming out of the restaurant, we have two big squares, our grease traps, which are required for the restaurant. Then we have open conduit gravity flow down to a central location coming from both the restaurant and the retail and apartments, where we have the pump system that is going to pump the wastewater along the roadway through a 2-inch force main. To find the pump to use for this, I had to develop a system capacity curve of head versus the flow. To design the head, it was mostly due to pumping it up at such a high elevation, about 50 feet. That was pretty much controlling. I also had to account for friction and minor losses, which I used equivalent lengths to calculate. On the right, we have the pump detail that I selected. It's a fairly large pump. It was one of the larger ones the company offered. It has to deal with, again, overcoming such a large elevation change. The pump manufacturer provides you with a pump curve, in which I had to impose the system capacity curve. We can see it's as we have a high head over on the left side, that's where our capacity curve lies, which is on the largest pump on that plot. For the grease trap, as I mentioned, coming out of the restaurant, the Department of Environmental Management requires grease traps to be able to have capacity for 50% of the daily flow from a restaurant. Our restaurant was estimated at 5,200 gallons per day. So dividing that in half, we needed 2,600 gallons per day of capacity. To achieve this, I selected two 1,500 gallon grease traps, which would look something like this, in series. And that pretty much solved all the wastewater problems for our site. Next, John McGowan is going to speak to you on the pier design.
Good afternoon. I'm John McGowan, and I will be lastly discussing the two coastal features that we presented in this project. The first feature is a fixed structure pier that will allow for pedestrian access to the water, and secondly, it will have a mooring area for boat passageway so the boat owners can go to our restaurant and retail areas for shopping. The two manuals that I used to design the pier are the CRMC Red Book and the FEMA Flood Insurance Study Maps. I designed the pier to withstand a storm frequency of 100 years and used a live deck load of 60 pounds per square foot. Two major calculations I did for the pier was to check the capacity of the decking for a 15-foot wide pier, and the second one was to check the capacity for the stringers running 16-foot spans in between the pilings. I used southern pine for my pier design, and I got the specs from the ASD Wood Manual 2005. Also, I designed the pier to the 100-year flood level, which is going to have a still water level of 13 feet. These are two views of the pier. The top view shows that the pier will contain an ADA gangway ramp that connects to a floating dock that allows for the boats for passageway. The bottom section shows the mean low water level and the mean high water level in reference to the pier and the ground surface. This is a cross section of the pier. The pier has 8 6x12 stringers that are going to support a timber decking. There's going to be 3 driven timber piles that support a continuous pile cap, and there's going to be a railing on the side of the pier. Lastly, the second coastal feature that I worked on was the revetment design. I used Hudson's stability equation to come up with results for the design of the revetment. For the primary armor layer, I got a 6-foot thickness, and for the intermediate layer, we're using a 3-foot secondary layer, and underneath is going to be 1 foot of 3/4 inch crushed stone wrapped in a geotextile filter fabric. The main constructability issue would be to match the top of the revetment to the grading of the site. And next is going to be Brett with some concluding remarks.
I would like to thank everyone for coming out today. I'd also like to give a special thanks to Professor Thiem, Mr. Russ Morgan, Mr. Mark Fisher, and Mr. John Steer, and of course GRA Engineering. At this time, we would like to open the floor for any further questions.
What was the maximum amount of fill you had to place and why?
Well, I don't know the volume, the height, I assume is what you meant. If I remember, I want to say it was actually underneath the restaurant because we had to dig down and remove the silt below that. And actually, since the glacial outwash was pretty close, we went all the way down there. I don't remember the number. It was like 20 feet, somewhere around there.
For the comparable with the previous group, I may have questions to drive. I'm sure you and then everybody took the CV347 and CV348. So we talk about the design factors for pavement structure. So could you tell us how you consider those, what was those design factors and how you consider those in your pavement design?
Well, of course, we took the medium dense sands into account, and then what else we used? We used the modulus. But yeah, it's only recorded all the numbers and stuff that we used for that design.
So, like at least you have 20% okay. You mentioned about the soil resident modulus. That's one factor you need to consider. The second factor you mentioned about design speed. And well, it's not really for the pavement design. Design speed is for the geometric design. One thing which a little bother me is you use 25 miles per hour. And then you also mentioned that that is the Rhode DOT practice, which I never heard about. Can you elaborate about where you got that, and then are you confident on your statement?
On the design speed?
Yeah.
Yes. Yeah, because it's a small road and then that's what usually done for asphalt.
Do you think the design speed is same as speed limit, or they are different?
Oh yeah, the speed limit would be 20, but the design speed is 25 because the thickness of the asphalt is what we use to get that.
So who will manage or maintain the road?
Who will maintain the road?
Yeah.
The owners of the site.
Yeah, so it's not Rhode Island DOT though. It's not Rhode Island DOT.
Well, we use the standards from them.
So the owner, consulting firms borrow the practice of the Rhode Island DOT.
Sorry, what's the question?
Did you borrow? Did you use the practice by Rhode Island DOT then?
Well, for like the width of the roads and stuff, yes.
All right. Thank you.
Okay, well, if there's no other questions, thanks.
Who's? Could went a lot better. Nah, could have went worse.
This is true.
Yeah, how the hell are my note cards all over the place?
I have
Just
no
the
idea.
one I
Yeah,
dropped.
yeah.
I made the scoop move in the second time around for it. I came back for it.
Good luck, my friend.
Thank you, alright. I appreciate
I
that.
have to say your project manager. I forgot that in the first question.
Did you?
I forgot that. No, at the bottom. So it's off right now? Stand by?
Yeah.
You want on?
What's that?
You want on?
All right. Is it right now?
Good afternoon, everyone. My name is Omar Abreu. I'm the project manager for Steel Stand Engineering and also part of the AutoCAD team. At the beginning of the fall semester of 2012, our Capstone senior design professors introduced us to a project where we will have the opportunity to apply all the disciplines of civil engineering. The preferred site is located in Tiverton, Rhode Island, to the west of Mount Hope Bay. And the reason why our professors picked this site is because one of them, who also acted as our client, Mark Fisher, was part of the team that actually developed what is of the site today. Sorry, guys. Hello. All right. So, as any project that would resemble real-world conditions, we met with the client and we went over his expectations, requirements, and the existing conditions of the site. Upon that conversation, Steel Stand Engineering determined that there were several challenges that we had to overcome. One is that along the site there's a railroad track owned by RIDOT, by which we had to leave enough clearance for a future commuter rail, and that led us to a design of a bridge and also an abutment wall. Our second challenge was, since our site is located off shoreline, we had to follow specific code and regulations. In this case, it was FEMA flood analysis. And by that, there was a couple of other challenges that came up with, from those calculations. One is the grading system, and second was a retaining wall. Our third challenge is that since we're treating this site as a virgin site, we had to come up with a wastewater system to pump out all the dirty water out of the site. Our client also mentioned that he wanted a roadway that would generate easy access in and out of the site for customers, delivery trucks, and also emergency vehicles. And he also mentioned that he wanted that road to end up at a boat ramp for kayak purposes. He said he wanted a restaurant to sit 120 customers, 6 buildings, from which the first floor would be used as the retail store, the second would be used as a condo. And he also emphasized that he wanted these buildings to resemble the New England architectural style. He said that he wanted the neighbors to feel comfortable with this new site development. Therefore, he wanted a recreational area, by which we determined that we're going to design a walk path that goes around the site and also a pier so that they can enjoy the nice view that this site has to offer. Now, to go into further details, I'm going to pass it on to our team members. To start off, I'm going to pass it on to Ethan, who is our AutoCAD specialist, and he's going to go over the site layout.
Hi, my name is Ethan. I was the AutoCAD specialist for this project, and here I just want to go over the southwest part of our project. Over here you can see we have our parking space right here, which is, why isn't it full?
I don't know why it's not full. I don't know, how do you do it? How do you do it? How do you do it? I don't know.
Did over there.
The middle one?
Yeah, that was the next one.
It's not showing. I don't know why. This week.
Right here, you can see we have our main parking area. This is for the restaurant, which is located here. We have a bridge down over here, but we're having projector issues, I guess. And so you'd come into the site over here, and you can you have to slow down over here for the crosswalk for the pedestrians, and you can make your way into the parking lot down over here, but it's messed up at the moment. We have a walk path that goes around the site, all over here. We also have a garden area right there, and a fountain over here. Our 6 retail and condo layouts are located over here, which is just above another parking area for easy access. It has the retail parking lot has 2 ADA spaces for handicaps, while the main parking space has 5, one of which is van accessible. And the road, although you can't see it, comes down over here and loops back up where you can turn around, and also where there is a boat ramp option right here where you can take your boat into the water in case you so wish. I'm going to turn it over to Ashley, who's going to talk about wastewater and grading.
Yeah, that's not even on. I'm Ashley Eads, and I was responsible for grading the site and managing runoff. Our main objectives in grading the site was to meet the client's demands, such as providing a flat grassy area that could be used for recreational services, to manage runoff effectively, and to keep the grade of the site as close as possible to the natural grade to minimize the impact on the existing hydrology. The first step I took in my grading process was to identify the property lines and mark off the property grades at specific points that the site was required to meet. Second, and most importantly, I analyzed the road profile because the rest of the grading of the site was completely dependent on the slope of the road. Next, I looked at significant structures, aka the retail condo buildings and the restaurant. The immediate area around the buildings had to be graded meticulously to make sure the area was drained properly to avoid puddling and therefore avoid future property damage. I also had to keep in mind the location of the buildings relative to the road to make sure I was allowing enough room to grade according to code, ADA and otherwise, and to allow enough distance to meet certain elevations. For example, we used 23 feet as our finished floor elevation for the retail condo buildings. The lowest point of the road directly in front of this area is about 16 feet. I had to allow enough distance between the condo buildings and the edge of the road to grade the parking lot at a 2 to 5% maximum slope, ideally as flat as possible, and still have enough room between the edge of the parking lot and the edge of the road to grade down at no more than a 3 to 1 slope so this area could still get mowed and further design would not become necessary, such as a retaining wall or a revetment wall. I also kept in mind, as far as the buildings on the site, I wanted to place them at a relative high point to avoid obstructions that would block the waterfront view from residents and clientele. Runoff was interconnected with the grading process. We used 3 best management practices to treat the water quality volume of the first inch of runoff as specified by the Rhode Island Stormwater Design and Installation Manual, Standards Manual. We used permeable pavement infiltration, except in handicap delivery truck areas and the steep sloping portion of the access road onto the site. We used a dry swale sand filter to treat the impervious water quality volume that was collected via yard drains and catch basins and pumped by gravity to the swale. The impervious water quality volume that was not pumped to the swale or piped to the swale was directed to qualifying pervious areas such as a large flat grassy area that would suffice as adequate water quality treatment. To talk further on our runoff analysis, I'd like to hand it over to Nathan Poutier.
Thank you, Ashley. My name's Nathan Poutier, and I was in charge of runoff calculations for the site, as well as wastewater treatment. Based on the IDF curve that is kind of cut off from Providence, we were able to determine the intensities for which we would have to treat the runoff of the rainwater. These on the right side are the values that are going to be flowing into our dry swale, as Ashley mentioned, through catch basins and a 12-inch conveyance piping. In order to treat the wastewater, we had to look at how much waste we were going to produce based on the 6 buildings and the restaurant, and we concluded that it was best idea to pump the waste up to the main municipal sewer on Main Road, Route 138. Since this flow had to be gravity pushed to the wet well in the valve pit, it's located at the low point on the site, and it would pump along the road up to the main line, about 2,000 feet horizontal distance from our site. This is the diagrams for the valve pit and the wet well that we're going to use for our site. 4-foot diameter for each. In order to overcome the head, the total static head it was actually about 140 feet, we had to use a grinder pump with a discharge diameter of 2 inches. And this is actually going to give us 24 gallons per minute operating flow, and our peak flows were calculated to be 16 gallons per minute, which satisfies the results. This is the system curve I developed based on that the factory manufacturer's pump curve and our total dynamic head. The operating point is going to be on where the black line meets the blue line, and for parallel pumps, since it's a auto coupling system, there's going to be 2 pumps, and if they are in parallel, the operating point would be at about 26 gallons per minute. I'm now going to hand it over to Alan, our transportation specialist.
Hello, my name is Alan Famaka, and I'll talk to you about some of the transportation aspects of our project. First, we designed our site for a WB-40 truck. It has an approximate turn radius of 40 feet. Here's our site. It's a little bit cut off. But as you enter into the site, the first thing you'll reach is our restaurant parking lot, and there'll also be a sidewalk located down the left-hand side of the road as you enter into our site. It then continues on to the retail stores, and then it continues down to our boat launch. And we're cut off here. All right. So you can see in our the cross section the sidewalk adjoining the road, and it will have a granite curb and it will be 5 feet wide. And then down below you can't see it, but as you continue onto our site, our sidewalk has a 5-foot grass buffer. Our restaurant parking lot has 57 regular parking spots with 5 handicap spots. The handicap spots are ADA compliant, and we have one van accessible spot. We have also a sidewalk that runs around our parking lot to keep people from walking through the parking lot. And from each access aisle in the handicap spots, there will be ADA compliant ramps to reach the sidewalk. Our retail store has 24 regular parking spots with 2 handicap spots, and both of our parking lots are made of a porous pavement. And our road is designed with a reclaimed asphalt. And I'll hand it over to Teresa Mulford.
Hi, my name is Teresa Mulford. I was responsible for helping Ethan out with a lot of the AutoCAD stuff, along with designing the restaurant and condo retail buildings with Omar. One of the challenges that we faced with the restaurant floor plan was that the Department of Health has certain regulations that controls where the food enters the building, how it gets served, and then also how it exits the building. Therefore, in our design, we were able to come up with a plan where the food enters the first doorway, a separate entryway, directly into storage space, where it then goes into prep and cooking area. It's served, and then through a separate entrance into the kitchen is then enters the dishwashing area, with a separate exit for disposal. That was one of the challenges faced in the restaurant, and I am going to pass it off on to Paul, who's going to talk about some of the structural aspects of the buildings.
Hi, my name is Paul Mendoza, and I worked on the structural team on the project. Quickly, I just want to highlight the structural aspect of this project. From the client, we were asked to design six retail condos, a restaurant, a bridge, and a timber pier. Here we have a retail condo. This is elevation view. We were just asked to design 6 1,000 square foot retail condos. Each would consist of 2 stories. And the first floor would be commercial retail space, and the second floor would be residential condominiums. Next, these are elevation views of the restaurant. We were asked to design for a seating capacity of 100 seats outside, 25 seats inside. Hold on a second. And we were also asked to implement the architectural style of the town. To do this, we added an atrium with a glass cornered wall, and this gave a nice view to the bay. Here we have some rendering from the Bentley's Ram Elements. On the left side, we have the condos, and on the right side, we have the restaurant. First, we had to determine the loads. We followed ASCE 710 requirements. Through those calculations, we determined that the wind loads would govern. Using those loads, we assigned the appropriate sections, and through that design, we assigned W sections for all the columns and beams, double angles for the roof trusses, single angles for the braces, HSS tubes for the atrium, and here we have the timber pier. The timber pier was asked by the client to allow access for small boats and also rentals for kayaks. The timber pier was a little bit different type of analysis, mainly because we haven't had too much experience with marine structures. However, for this structure, the design load was the lateral wave force. After reviewing the FEMA flood insurance and using linear weight theory, we were able to determine the lateral wave force, and we also determined the axial capacity of the piles. The dimensions of the pier was 200 feet long, 6 inches in width. The piles had a diameter of 1 foot and were 30 feet long, and they had bents which were spaced at 15 feet. For the timber piles, we used Greenheart, which is good for marine structures, and it's really good at preventing decay. And yep, that's all for the timber pier. And now I would like to pass it over to Tomas, who will talk about the structural analysis and the bridge.
Hello, my name is Tomas Perez, one of the structural engineers for this project. To start, our client asked us to design a bridge. The The reason for this was because right under the road that provides access to our site, we have a Rhode Island DOT right-of-way, which we actually had to make sure that whatever structure we built there complied with the clearance requirements for a possible railroad that they would have liked to include there. Once we found the clearance envelopes, we realized that they were curved, and actually this served as an inspiration to the design of our bridge. Here's an elevation view of our bridge. Basically, it consists of an arch. It spans 48 feet. It has 6 bents spaced at approximately 7 feet each. The bents consist of spandrel columns, which are holding up a beam, and these altogether are holding a concrete slab. The whole structure is made out of concrete, and here's a detail of the cross section. As you can see, our transverse beams were 12 by 18. Our slab was a little thicker than usual. It was 11.5 inches, and the reason for this was because in this case, as opposed to most bridges, we have transverse beams holding up the structure, which in most bridges it will be the other way. It will be longitudinal. Then these sit directly on top of both of our 2 arches, which then transmit the loads to the abutments. Now I would like to talk about the overall structural analysis and design methodology that we used for all of our structures. Essentially, we used a program, RAM Elements, and first of all, we based on the plan views of the restaurant and the condos that Teresa and all the other AutoCAD guys had designed. We came up with possible structural models of all of our structures. So after that, based on the different codes, in the case of the buildings, it would be the ASC 710. In the case of the bridge, it was the AASHTO manual, AASHTO Bridge Design Manual. We came up with all of our loading conditions. Everything was designed according to LRFD specifications, and we applied the loads. These were all hand calculated. Then we used the program to come up with basically envelopes of what the worst case scenarios were for each of these loads. In the case of the bridge, we actually had to simulate moving loads because the program that we used didn't have those capabilities. So we had to create different loading cases for basically simulating a truck being here, then at the next maybe moving a little forward and figure out which one of these was the worst loading condition. These were all backed up by hand calculations, which we used to kind of estimate what our loads would be if these were simpler structures. Finally, based on these, we used the design capabilities of our program to come up with the members and this is for the case of the buildings. In the case of the bridge, we used the ACI manual along with the AASHTO bridge design requirements for all of our reinforcement design. When we did finally, to make sure that everything was okay, we also came up with our own spreadsheet that checked the capacity of all of our steel members. And this is just to make sure, for quality assurance purposes, to make sure that all of our designs were actually safe. Now, I'm going to pass it up to Dan Geets, who is going to speak about the supports of all of our structures.
Hi, how you doing? My name's Daniel Geddes, and I worked along with Jason Leonard on the geotechnical aspects of the site. Some of the things that we were asked to design were an abutment, retaining wall, and first thing I'm going to talk about now is a little bit background, the geology of the site. One of the first things we did was consulted RIDEM maps, and we found that the bedrock of the area falls under the Narragansett Bay Group. The primary rocks for this being arenite, which is a classic sedimentary stone, and shale. which is a fine-grained sedimentary stone, both of which can be seen in the preliminary boring log investigations. From these boring logs, we were able to create a soil profile. This soil profile is from the area of the abutment, and some of the material that we found when investigating this was fill on the top, glacial outwash, some organics and silt, as well as glacial till, and at the bottom, weathered bedrock. Okay, for this soil profile, once again, this is from the area of the abutment. We were able to use this to come up with data in order to use that for parameters pertaining to the abutment. And I'm going to pass it off to Jason really quick to talk about the bridge abutment.
Hi, I'm Jason Leonard. I was another member of the geotechnical team. And this is our proposed cantilever bridge abutment. You can see here the soil is acting on the abutment. We initially looked at only active earth pressures, but when we found that the sliding factor safety controlled, we decided to install a shear key, which you actually can't see. It's at the bottom of this this figure. This allowed us to get passive resistance from the railroad side of the abutment. And here you can see the active and passive earth pressures, as well as the surcharge due to construction equipment on site during the installment of the abutment. And we designed it using ASD standards, and it satisfied the factors of safety for sliding, overturning, and bearer capacity. And the final dimensions were a final height of 33.6 feet, a base width of 22.4 feet, and a stem width of 4 feet. And I'll now pass it back to Dan, who will talk about our geogrid wall.
Okay. Oh, it's a shame it's cut off. But so another thing we were asked to design was a retaining wall. So for this retaining wall, we decided to go with a geogrid wall. And this is a plan that we came up with for our proposed geogrid wall. We have our block detail, drainage detail, some information about the material that we specified, and some general notes pertaining to material as well. It's a shame you can't see it, but at the bottom of this we have a drainage detail, and this is our wall face, our geogrid layer, and some impervious fill. So for this we we used the Stone Terra MSC Wall Systems Engineering Design Manual. And since this was like the first time that we had gone about designing something like this, we found that manual to be pretty useful. We decided to go with a StrataGrid 350 geogrid fabric, and in doing our calculations, we checked for the external and internal stability of the wall, and for the internal, we checked the pull-out resistance of the geogrid, and we decided to go with uniform lengths for each one of the geogrid layers. Okay, so now I'm going to pass it over to Jason again to discuss foundations.
Another thing we did as a geotechnical team was we designed the foundations for the buildings on site. And we did this by getting the unfactored loads from the structural engineers, and then we combined them using LRFD load combination equations. And we use these max loads to design the footings themselves. And we took into account the frost depth when designing the footing, so we made sure the base was below the frost depth, so that wouldn't be a problem. For our final design, we ended up with 4x4 square foot footings connected by an 8-inch bearing wall. And this is actually the foundation plan for the condo/retail buildings. And now I will pass it back to Omar for closing remarks.
Well, thank you guys. As the team members mentioned, we designed all the tasks that our client required, and we also use all the proper codes and regulations for each one of those designs. Therefore, still Stan as a group feels that we have exceeded his expectations. We would also like to take the opportunity to thank our professors for providing us a project of this magnitude. And we would like to thank our mentor, engineering mentor, VHB, for being great help throughout this project. And also, last but not least, Steer Engineering. This is the end of our presentation. Thank you for your time, and now we're open for questions.
choices for dealing with the wastewater, right? They can pump it off site, which is what you do, or you can treat it on site. I'm just wondering what went into your decision to pump it off site.
Not only did it seem cheaper, but it also avoided the issue of the structural loadings around our site. We weren't sure exactly where everything was going to be placed, and so we decided pumping was the best option at the very beginning of the year.
And one other question, which is out of my area, I'll ask it anyways. On the concrete arch, did you have steel in there for the bridge? And where was the steel placed?
There was first of all there was steel, and to talk about the details, that's not sure.
Do you want number four?
No, just verbal.
Well, okay, yes. Essentially, the concrete arch, for the most part, is a compression member. Therefore, you would treat it as such. And it has a very short embrace length. It's basically the length from one bench to another one, which is about 6 feet. So really, you would design it for the most part as a column. You do have to take into account shear, and the stirrups would take care of that. So yeah, you would just design it the same, follow the shape of the arch, the same way that you would do a column.
You know, first of all, congratulate your group. Good job, like previous two group. Because when I asked questions, that doesn't mean you did not do a good job. You did a good job, okay? However, we want to make sure that you will be, confident on what you are doing. So, as you expected, I think next question will be to the island, I guess. So, you showed the one slide, cross-section of pavement structure.
Yeah.
But in some reason, I cannot see well, because I guess my eyes are like this.
Yeah.
We have to consider my technical issues.
My question is, what kind of material we use, and then how thick the structure was?
Yeah, we used reclaimed asphalt, and it was 1.5 and then 6.5 inches thick, and then an 18-inch sub base.
But when you say the reclaimed asphalt,
yep,
you use 100% reclaimed asphalt, or the percentage of asphalt content? You said you used reclaimed asphalt.
Yep, there was
Did you use 100% for the surface?
Oh no, not 100%. I think it's about 8% reclaimed asphalt.
80%?
No, much smaller. I can't remember off the top of my head, but it is lower. They do have to use virgin material, but it does help in the design to reduce the amount of.
When you are getting the asphalt concrete from the asphalt plant,
yep,
you need to tell them what kind of asphalt I want. Okay? So one of them is in Rhode Island.
Yeah.
If you go outside the Rhode Island, they don't understand. They are saying Crest I1. Okay? So if you do not hear about Crest I1, you'd better be familiar with Crest I1, what they are talking about.
Okay.
If you want to stay in Rhode Island.
All right.
Okay. Thank you.
Okay, that's it. So thank you very much.
I don't know where that is.
So I have to leave by within 30 minutes. My wife is waiting.
You should plug it in anyway.
We have to be out here.
Just in case. We don't need any fuck-ups like that.
Our church has picture.
All right, let's work on the screen resolution, shall we? That actually doesn't look, it's cutting off a little. It's under resolution, right?
Yeah, that would be it.
Do I have to go lower?
No, try this 1280/60.
Maybe.
Very cool.
Very nice, very nice. He changed his gear. Okay. Cool.
There we go. Flip through a few just to make sure it's working. Alright, sweet. Good to go. Yeah, I think we're Chris, do you guys flip the slides? Good afternoon, everybody, and thank you for coming out. My name is Eric Stamp. I'm project manager and one of 2 structural engineers for Advanced Consulting and Engineering. Here's a snapshot of our team and our team layout. Each member will introduce themselves as they speak. Here you can see a locus plan of our site development project. It's located at the end of Schooner Drive in Tiverton, Rhode Island. Here you can see a satellite view of the existing site conditions. You can see that it's a completely virgin site. And our project overview consists of our client, Mr. Mark Fisher, who prompted us to take on this development. Our consulting engineers were Dr. Leon Thiam and Mr. Russ Morgan. Our scope of work included developing a virgin site, cutting, filling, and grading the site, extending Schooner Drive through the site to meet all the needs of the site, constructing parking facilities, erecting various residential and commercial structures, constructing a bridge as means of entry to the site over Rhode Island DOT right-of-way, and implementing all necessary environmental devices to service the site. And now I'll pass it off to Sam to talk about site layout.
Thank you, Eric. My name is Samuel Payton. I'm part of the AutoCAD team for ACE Engineering. As you can see here, this is our site development. To the far left is our restaurant structure. Adjacent to those are 3 retail residential structures for immediate construction. Across the small gap in our development is our other 3 retail residential structures, which will be slated for later construction. Here you can see our parking lot. We decided to wrap it around our buildings to accentuate the arc shape that we created. To the far right is our boat parking for trailers to leave trailers while they use our boat ramp. Around the edge of our site is our gravel walkway for access to the shoreline. And here we have our road structure flanked by 2 retaining walls. Also, at the far edge of our site, we use retaining walls to aid in the grade change from our building elevation to existing. For our site, we had a few challenges that we wanted to accomplish. First of all was our site development, mostly our grading. FEMA regulations state that all buildings must be above a 100-year flood level. For our site, that was about 20 feet. So as a solution to this problem, we decided to use cut and fill and also retaining walls to aid in these transitions. Our environmental concerns for this project dealt mostly with water and stormwater and wastewater treatment. The problem we had was to decide whether to treat on-site or off-site. For our access to our site, we had to develop our road alignment, our ADA accessibility, and also our parking. Here you can see a 3D representation of our proposed site. For the beginning of the grading, we had to set all our buildings above 20-foot elevation. We decided to start with our restaurant at an elevation of 21 feet, and our 3 adjacent structures next to that also at an elevation of 21 feet, and step the other buildings down to an elevation of 20 feet. This coincides with our 1% grade in a northward direction
to convey our runoff towards our detention basins at the far right. And also, we put a 2% grade away from the buildings to meet up with our roadway as it comes down to grade. This is a different view of the same site, facing a southerly direction. As you can see, it shows how the roadway comes in from a much higher slope and matches up with our proposed site. And now I'd like to bring up Luis, who will talk about our road grading.
Thank you, Sam. My name is Luis Gonzalez, and I'm here to talk about the elevation changes on the road. When we decided to draw the alignment here, we decided to have a critical point on the intersection of the first entrance of the parking lot at 18.5 feet. Using the 6% grade coming from the existing Schooner Drive, we had to dip it down even lower to an 8% after we go past the bridge. At station 600, we changed it to 6.04% until it meets 80.5 feet in elevation at station 750. During this transition, the super elevation of the road is towards the right, to draw the water to the right into the little hole. After meeting the height and grade 1% on the parking lot, it runs at 1% all the way through the system of the road. At station 1300, you can see that it raises up again. It's still at 1%. This is because it's the rotary on the end of the road. This is done so it can latch back into its height when it comes back. The rotary is measured at 12 feet wide for a one-way throughway, but it also has a 16-foot buffer zone for back-drilling wells designed for delivery trucks, wide-turning boat ramps, trucks, boats, and any other emergency vehicles that can use of it. It also allows the fluidity of the driver to go to the parking lot and come back. Also, there's another entrance for the main parking lot from this location. Go ahead. When we're dealing about elevation changes, especially with adjacent to each other, and the fill that's used to raise the building sites, the building areas, rotation walls have to be considered. 3 locations were devised, and one of them is behind the restaurant and the first 3 set of commercial buildings. The second one is behind the second set of commercial buildings. And the third one is for the first 800 feet of the road on the inside and outside of the road. Now I'll lead you off to geotechnical specialist Dan Litton.
Thank you. Again, I'm Dan Litton, and I designed the retaining walls of this site. This is a rendering of the retaining wall behind our retail buildings against the seaside. So in order to design this, I picked a worst case scenario through iterative designs, and I filled the back of the retaining wall full of water as if the drainage was full. This created a need for that shear key at the bottom, which is 3 feet deep. Seems very large, but if you look at the volume of concrete compared to what we would need for high enough factor safety against sliding, it ends up being conservative in our volume of concrete. We also use redundant systems to prevent that fill of the back of our retaining wall through a drain under the heel of our retaining wall and weed poles spaced at 10 feet along the length of our wall. This is a slide 6.0 seepage analysis of that retaining wall. It shows that the water will flow from up to down, obviously, and give us an upward velocity at the bottom of our wall. The upward velocity was then used to calculate the seepage forces and a factor safety against piping and erosion. We ended up with a factor of safety of 6.5 against piping and erosion, which makes this wall very safe against that. In between those retail buildings, we have an 80-foot slope with a 10-foot grade change. We also put this into slide 6.0 to calculate the factor of safety against an infinite slope failure. Sands characterize an infinite slope failure due to their high effective friction angle and low cohesion strengths. In our slope, we have a factor of safety of about 6.25 against failure, so we have no problems there either. Now I'm going to give it to our environmental team.
Hi, I'm Cassie. I'm an environmental engineer, and a major concern with the project is that with the site development, we want to impact local ecosystems or hydrologic processes. So first we determined the impervious area with the roadway, parking lot, and roof workshops. We referenced the Rhode Island Stormwater Design Installation Standards Manual, and we met all water quality requirements and recharge requirements. A design feature for the stormwater is that we can effectively convey and treat a 1, 5, and 10-year storm. So for our design, we had a swale and 2 bioretention basins. We wanted to maximize natural conveyance, so the swale is located in between the parking lot and the roadway, and both surfaces are pitched towards the swale. The stormwater is going to run underneath the entrances to the parking lot through a culvert, and there's going to be riprap on the entrance to reduce solids that could enter the culvert. We designed the swale to have a 2% slope so that there is no erosion, and it's going to be our pre-treatment for our design. And the secondary treatment is going to be the fire retention facilities, which is going to have a 2.5-foot bioretention soil. And with larger storms, like a 10 or maybe 50-year, the flow is going to go towards an existing outfall that is located on the northern end of the site. Like I said, we wanted to reduce the impacts to the hydrologic processes, so we developed hydrographs using HydroCAD. You can see when the water enters our system with the impervious cover, there's a high peak flow. And by the time it runs through the system and exits the bioretention facilities, the peak's going to be low and more gradual. And I'm going to give it off to James for wastewater.
Hello, I'm James Gallant. I designed the wastewater treatment system. Me and Cassie were working on our environmental layout and our design goals. We kind of wanted to try to maximize natural processes. We examined briefly pumping up to the top of 138, but there was a large head, and we realized that we had the space and a good CAD team, so we were able to come up with a configuration to treat all of our water on site. Due to the grading, I ended up actually separating the 2 on-site treatment systems. I hooked up the 6 residential and commercial structures to 1 independent system, and the same for the restaurant. I designed this in accordance with the DEM on-site wastewater treatment manual, and those values were derived from Rule 22. This is a schematic of our residential and commercial on-site wastewater treatment system. I designed this so obviously we have 3 immediate and 3 future builds. I designed this so that they could be easily tied in, and our leach field goes out to a pretty open space, which after we kind of looked at the site configuration, we realized that within our constraints we would actually be able to treat all this on site with quite a bit of space to spare. Our leach field is comprised of gravel dispersal trenches. They're about 1.5 feet deep, and they have 4-inch perforated PVC pipe running throughout their lengths. Again, schematic. And this is our restaurant on-site wastewater. Obviously, a restaurant, you have grease production, so we employed a 4,000-gallon grease trap that lags into an 8,000-gallon septic tank. And this is a zoomed-in version. The leach field is actually designed. The design process was the same. It's just much bigger because the design values for our restaurant were significantly higher than that of our 6 residential commercial structures. So the basics of the leach field and the design parameters are the same. It's just on a larger scale. So I'm going to introduce Kevin Don, our transportation guru.
Hi guys, I'm Kevin Don, transportation engineer. So before we actually design the structures, we will actually have to consider access to the structures. So through trip generation, I approximate about 1,000 vehicles per day for the site. So the total roadway length will be approximately to 1,600 feet. Total width of the road is going to be 26 feet with 2 12-foot shoulders. And we're going to have 1 sidewalk on the west side of the road. So according to this road cross-section at station 550, our slopes our roadway slopes are going to be 2%, which will lead our runoff to the swales that's to the west of this. For horizontal curve alignment, we needed to provide a minimum radius for, say, a WB50 truck to be able to turn into use the access road and turn into the 4 access ways of the parking lot. And we determined the minimum radius of 125 feet, which is greater than the actual requirements of 71 feet for a speed of 20 miles per hour. And to verify our results, we used auto turn. We tested 3 vehicles: a WB50, a fire truck, and just a regular vehicle to maneuver through our site and analyze if we provide enough space to maneuver around. So, for our site, we need parking spaces. And according to the town of Tiverton, we calculated 110 parking spaces. As you can see, this is how we calculated the parking spaces, but and here's our general main parking lot. So for our pavement profile, we decided to have asphalt pavement. We did not consider permeable pavement because of the amount of fill that we're going to be putting on the site. According to Ryan DEM, we can't allow, we're not able to use permeable pavement. And for our main parking lot, we're going to be using the heavy-duty asphalt design. And for our road, for the road, it's going to have heavy-duty asphalt design. And for our parking lot, it's going to be the standard asphalt design. And this standard was given to me by the pre-engineering. For our site, we have to consider ADA. So whenever feasible for the structures and the switchback, we're going to have a 1 to 12 ramp slope, a maximum width of 48 inches for the pedestrian ramps and handrails on both sides. So some transportation challenges include pedestrian accessibility and safety, parking difficulties, and speeding. Some recommendations I would include is traffic calming techniques in the parking lot, speed bumps to reduce parking and to improve pedestrian safety, and the Serpentine Road, which is a reverse curve to reduce speeds. Next. And now I would like to introduce Chris London.
Thanks, Kevin. So, my name is Chris London. I'm a structural engineer on the team. We're going to get into one of the first challenges we had with designing the project, which was the entry to the site, and we used a bridge across the Rhode Island DOT Roadway. Displayed here is a 3D model instead of the bridge we used. We'll get into a little detail about it in the next few slides. So here's a basic cross-section of why we needed the bridge. We have a certain elevation on either side. The DOT needs a 23-foot clearance in the center here for rail and a potential bike path, and we had to maintain that. So we have approximately a 50-foot span and 23-foot clearance, as I mentioned. Here's a plan view of our bridge, basic 12-foot lanes. You can also see on either side we have a cantilevered crossway for pedestrians. This is going to be a timbered decking across this and an ornamental railing on either side to keep up with the aesthetic look of the site. And here's a cross-section and longitudinal section of the bridge. You'll notice again the ornamental railings and side walks for crossing pedestrians. This is a truss bridge. We used all steel members for this bridge. And now we're going to pass it off to Eric to talk about the restaurant.
So per request of the client, we had to design a restaurant that can seat 100 occupants indoors and 30 outdoors. The frame you see here is our 3D rendering. We used an all-steel design, steel roof trusses, and we used X bracing to take wind loads and moment bracing in the front moment connections to take the wind loads where windows were invading on possible X bracing. Here you can see a plan view of the restaurant. It shows all the amenities we included. It's approximately 5,900 square feet. Here you can see elevation views of our restaurant. The top view is the land side, showing the entrance and a cutaway of our steel stud framing and steel house roof truss. The bottom view is the seaside, where you can see we have pervasive windows, so the views are not forgotten about. The patio is shown for the 30-seating outdoor dining. Our analysis included determining our member loads instead. We chose our loadings with our LRFD, and we applied them instead. We confirmed them with hand calculations, and then we utilized STAD to optimize the members. And when we optimized the members, we found the worst case and carried it through the structure for simplicity of construction. Our final member design, all the columns were W10 by 77s. The cross bracing were double L8 by 6 by 7/16 inches thickness, and the beams were all W10 by 49s. We had our steel house truss roof design, and the floor was a concrete slab on grade. I will now bring Chris back to talk about the retail.
Yeah, so we spoke about the 3 major retail and residential buildings that we are having for immediate construction. Displayed here is another 3D rendering that was performed in STAD. You can see the cross bracing on the sides that weren't crucial to have windows, and where windows were necessary, where the seaside view was important, we used mobile connections. This is the plan view of the retail. One of the challenges we had was parking coming from the rear of the building and the seaside views in front. So we want customers to have access to the parking and then be able to go out to the front and enjoy the water as well. So what we did was a dual entrance on either side. And this kind of limited us in our cross bracing, so we needed a few more mobile connections, but we felt it was worth it. This is a plan view of the residential building, apartment. It has a master bedroom, a spare bedroom, living area, kitchen, bathroom, and dining area. And here you can see the elevation views. The west face would be towards the water, east face is away, and south face is facing the restaurant. So the analysis for the retail and the apartments is very similar to the analysis in the restaurant. We ran through all the code books as far as ASCE 7 for the wind loading, the Rhode Island State Building Code, International Building Code for all of the other regulations. LRFD load combinations were determined, and we plugged all of those load combinations into STAD to determine the loads in each member. These loads were confirmed with hand calculations, and then processed in STAD to optimize the steel members once again. The table here shows another summary of the structure. And also in the STAD output, we were able to determine the reaction loads and nodal displacements, and this helped us to find the column loads to pass on to the geotechnical team. And I'm going to pass it on to Rob to talk about the foundations for each of the buildings.
Hello, my name is Rob Mandalara, and I'm part of the geotechnical team. After the site investigation, the geotechnical team analyzed the soil properties. We determined the existing soil properties were good and that they were suitable for shallow foundations. Neither deep foundations nor ground improvement is necessary for the site. Shallow foundations transmit structural loads to the soil underlying the ground surface. Then there are 2 different types of shallow foundations, spread footings and mat footings. Mat footings are necessary with poor soil conditions and high structural loads. We had neither. The loads of the structures were similar and relatively small. Therefore, spread footings were chosen. To determine the dimensions of the spread footings, we combined terms from Terzagh's bearing capacity equation, the weight of the proposed footing, as well as a factor of safety of 2, and the structural loads applied by the structural engineers. The geotechnical team designed the dimensions of footings to be approximately 2.5 feet, but for constructability and economic reasons, we rounded up to 3 feet. The depth of the footing is at 4 feet for frost protection. Now to introduce you Greg Corey, he will go over the details of the foundation.
Hi, I'm Greg Corey. Since I'm a geotech, I'm going to start from the soils and work my way up the structure.
I'd like to characterize the soils in this area as being sand mostly. There are some sand and gravel areas. That's characterized from approximately ground surface to between 5 and 45 feet deep. At some spots in the locations of the actual structures, there is some siltness in with the sand. However, it's beyond 45 feet deep, so the appreciable stresses in those layers are going to be negligible. For this reason, and for the constructability of these footings, the 12-inch lifts are going to be put in of soil beneath them and compacted to 95% relative density. This is going to eliminate any chance of settlement in the sand, so there really isn't going to be any settlement underneath any of these footings. Moving up to the actual structure itself, the footing was back calculated, the size of the footing was back calculated using Terzaghis bearing capacity theory for square foundations. As Rob mentioned, it went from 2.5 feet to 3 feet. The 3-foot column had to hold a maximum load of approximately 75 kips, so relatively light structures. And what this did was, over a 3-foot square area, it came out to about 60 psi in the ground surface, so really relatively low. Most of your running larger trucks, they put out about 100 to 120 psi in your ground surfaces. Some performance tires on a light car put out 65, so it's quite light, the actual bearing on the soil. So we used standard ACI reinforcement design in the concrete. The thickness of the actual footing came out to be 1 foot 8 inches. And the depth, 15 inches. And the depth of the actual rebar was 12 inches. So moving up to the column, between the interface between the footing and the column itself, we provided a raked construction joint for phased pours for the concrete. As some of you probably know, you have to wait 7 days after pouring the first phase of a pour to pour the second before it bears any load. So the footing would be poured, and then 7 days later the column have to provide a raked construction joint in order to achieve shear. The column is actually way oversized, and there's a couple reasons for that. In the initial design, the 75 kip load based on the column yielded quite a small column, smaller than the base plate for the steel column that we have constructing the membrane of the building. So what we did was we designed the column, we came out with our actual minimum gross area for concrete, and we increased this until we had enough area on top of the column here to support both the columns in the body of the building, the base plate, and any fascia boards from the light gauge steel framing that we're going to have to construct the skeleton of the building. So you can see that the column widths actually came out to about 22 inches by 22 inches. Since the load was so low on top of these columns, it practically required no steel. What we did instead was we added number 5 rebar at 4 locations to give us some rigidity and some shear strength, extra shear strength. You can see that those are embedded both in the footing, so that's the phase construction that I was speaking about before. You pour those in the first half, they stick out exposed until you're ready to pour the second half. We designed the columns as tied square columns, so you can see down here we have the 4 number 5s at each corner and then internal ties. That accounts for ACI code, in which if any bay between rebar is greater than 6 inches in a tied column, you have to provide internal ties such as those. I'd like to bring you to the top now, to the top of the actual concrete column where it meets the base plate. We have a detail here in which the base plate connects to the concrete column through 4 3/4 inch anchor bolts. They have leveling screws in the bottom in which the base plate sits on top of. You level those during construction, then you add your top nuts, tighten those down to your required torque, and then you hand pack grout underneath the base plate in between that and your already poured column to ensure that the anchor rods are not supporting all of your downward force, that you actually are getting bearing in the concrete. On top of that, as I mentioned before, we have the steel column and the light gauge metal framing that is going to form the skeleton of the building, and on that we have a detail for the cedar shingling that will be on the outside. With that, I'd like to turn it back over to our transportation specialist, Kevin Don.
So after considering structural design, we also, according to our client, this site will also be used for recreational use, outdoor use. So we considered a pedestrian walkway. It should be 10 feet in width, and the soil surface should be 2 inch material, then compact under our 6-inch gravel. And I also want to let you guys know that no matter where you guys are at the site, if there's a restaurant, walkway, commercial buildings, you will always have an ocean view, and if you're at the right time, you have a sunset view. And now I would like to pass on to our project manager to conclude our presentation.
So in conclusion, our client, Mark Fisher, he prompted us to undertake this development project, and through our proposal, we've shown that we developed a virgin site, we cut, filled, and graded that site, we designed a roadway and bridge as a means of access to the site, we designed the buildings per the client's request, and we designed all the environmental measures to service those buildings and structures. I'd like to conclude our proposal, and I'd like to give thanks to our professors, our assisting engineers, our consulting firm, Dupree Engineering, and everybody who is here in attendance today. And I'd like to encourage anybody after the presentation to view our plan files, and we will now take questions and comments.
Environmental questions. 3 out of the 4 groups pumped out of the site for the wastewater you guys treated. I'm just wondering if you were working for me, in fact, as a client, why you convince me that your method of treating the waste is better?
Well, we actually cost estimated it, and it looked like it was going to come out to a little bit less to actually go up. I mean, you were fighting a pretty large elevation change. So you would require a pump with a good amount of head. Obviously, you'd have to have a redundant pump as well. Up to 138 from the proposed area of where we would have had the pump, it would have been about 1,900 feet. So it would have been a pretty long trench up to the main road. So we kind of figured that treating on site was the best option available to us. The maintenance costs are relatively nominal, and those are logic behind it. That's good.
If I could just add one thing to James. One of the things that was considered in the design of the actual environmental system was the emergency response. If you have a pump system that fails during any type of power outage, you don't have that problem with fire retention system like we designed.
It was overall very good project. However, I have one comment and question to Kevin. I noticed you for protection indicate binding layer, but we used to use the binding layer in Rhode Island, but about a couple years ago, Rhode Island DOT decided not to use anymore. So we still can get material if you want, but you may not get that binding, the asphalt concrete for binding layer from asphalt plant. So you may delete that one and then use soft this layer and then the base layer, 2 layers, it's a 3 layer, 3 asphalt. And the question would be, what kind of approach or guide did you use to determine the thickness of pavement structure?
There was 3 guides in use. The first guide was 1993 flexible pavement axial empirical formula in the nomograph, and I assumed certain factors like equivalent single axle loads of 500,000, serviceability index of 4.5, and terminal serviceability index of 3, and assumed values of MR, and
it was 1993 design guide.
Yes.
But now
that was
we have
the first
new one
approach.
now, right?
That was the first approach. Second approach was provided by you, the 2008 hot asphalt mix design, and considering it's going to be a local road with less than 1,000 ADT, we're going to have a base of 1.5, surface layer of 1.5 inches, a base of 3.5 inches, and over the compacted fill, and using 12.5 millimeter clay mix. And the third method I used was my consulting firm, Dupree Engineering, who gave me minimum requirements. And after the 1993 pavement design, empirical equation calculations, it did not meet the requirements given to me by Dupree Engineering. And for simply mix design, I the sub-base and base requirements was under the pre-engineering guidelines that was given to me, so I decided to use the pre-engineering guidelines.
Well, it was good, I think, but you missed one. It's 1993 means about 20 years ago.
Yes.
Right? So about 10 years ago, we got a new pavement design guide, so-called mechanistic impartial pavement design guide. If you probably you don't have to use because your road is very low volume road, but the MDPDD is a high volume road. But you can check, okay? You can find this. You can use that MDPDD. You may not need to use eventually. So you are using like a design guide for low volume road, but it was good if you tried. Okay? Thank you.
Good. Thank you very much.
Good job. You held it together. Proud of you. Professor, we're going to leave our sticker.
Yeah, okay. Can you take that?
You want me to hold it?
I got it. Okay, let me just make one more announcement before we close. Really some thanks. Thanks to the mentoring organizations, Gordon Archibald, Crossman Engineering, Deprete Engineering, VHB, who are also in the audience there. I'd like to thank Brian Giroux, John Steer, who's over there. I'd like to thank the two faculty judges, civil engineering faculty judges, Professor Bradshaw and Lee, and a really special heartfelt thanks to Russ Morgan over there. So thank you, Russ. Thank you, everybody, for helping us. Okay, so this concludes our presentations for today.